And so this is why you shouldn't take my title completely literally. So the title is Finding the Equations of Behavior. And that's really what I do. That's what I do for a job. I look at animal behavior and I try to find out what mathematical models best explain different aspects of animal and human behavior. The point here is that this really is as much an art as a science. There's a lot of creativity involved in trying to model things mathematically. There's creativity in deciding what sorts of things we're going to model, and there's creativity in deciding which models we're going to use. So we like to think of ourselves as creative people in the way that we use mathematical models. So what do we do? Well, the top left-hand picture there is a couple of ants, and one ant is teaching the other ant where its nest is, where its new nest site is. The right example is also in ants. They've left a pheromone trail between their nest and food, and they've managed to find the shortest path there. This example is fish swimming in a school. This is an example we did of an experiment on people and gaze-following behavior in people. And what we do in all of these cases is we film the animals or the humans, and we try to analyze their behavior in various ways. When we can understand how the individuals interact with each other, we can build up mathematical models which describe those interactions. This is a model we had of how the ants decide to move left or right, depending on the concentration of pheromone. This is an illustration of a model we had of how the redfish decides to move left or right, depending on its distance to the wall and its distance to its neighbor. So by tracking and looking at the videos, we can understand which interactions lead to which collective behaviors. We're trying to look at individual interactions, build a model of behavior, and predict what's happening at the global level. So the coupling to art, which I mentioned, is that what I think that mathematical models are trying to do. Why are we creating mathematical models? Well, my answer to that is that mathematical models enhance our understanding of the world. And I had this title at the start that I'm trying to find the equations of behavior. And I think a common objection that members of, I suppose when I go to dinner parties and things like this, people say to me things like, oh, you can't expect an equation to explain behavior because our behavior is so much more complicated than that. We fall in love, we have all these complicated relationships with people. You can't expect an equation to explain that. You say to me that describing the world as an equation misses all its important and beautiful complexities. My argument back to that would be like saying to an artist, if you said to an artist, representing the world as art misses all of its important and beautiful complexities. People at dinner parties don't tend to say that sort of thing to artists. They say it to mathematicians all the time, but they don't say it to artists. Because the idea with art is that you're trying to capture all of the beautiful complexities of the world. And so the way I see using mathematics is very similar to the way that people see using art, that we're trying to enhance our understanding of the world. So that's some of the philosophy behind it. What I'm now going to do is whiz through a lot of examples where we've done this kind of thing. And I'm going to start with a model of popularity. It's the pop chart gravity model, I call it. And you don't need to take in all the equations, but what these equations are actually Newton's equations of motion. And I wanted to test the idea, do songs go up and down the charts in the same way as a projectile goes up and down into the sky? And I wrote a little simulation to show this. This is a Swedish favorite, of course, coming from Sweden, or living now in Sweden. I thought I'd show this. But this is plotted on the x-axis is time, that's weeks. And then on the y-axis is the position in the charts. And the dots there are the data, and the line there is the perfect mathematical equation of motion for a projectile. And you'll see that it does quite well at going through the data. And we can take different songs here. You can go and play around with this online later at the webpage. And there's Like a Prayer by Madonna from the 1980s. Eternal Flame from the same year. This is one from me when I was about 10 years old. This was Take On Me by a-ha. We can go back in time. This is All Shook Up by Elvis Presley. And you can see that for all of these songs, with a different entry-level velocity and gravity, this gravitational model is a very nice description of how these songs went up and down the charts. If we look at more recently, we see actually the charts have changed. If I take Like a Prayer by Madonna, it went in quite high, it had a high velocity, but it also had a very high gravity pulling it down to earth. But if we look at Poker Face by Lady Gaga, we see that it went in reasonably low, it had a high velocity, but it had a very, very low gravitational pull. So we can actually see how gravitational pull in the charts has changed over time. And I was a bit surprised at this, but we actually have a longer concentration span for songs now than we used to have 20 or 30 years ago. So the gravity is a lot weaker on songs like Lady Gaga, on this is Viva La Vida by Coldplay. This was thrown into the charts very high, but it just stayed with an extremely low gravity. And that's very common. This is I'm Yours by Jason Mraz. I don't know anyone who wasn't extremely annoyed by this song on the radio after 2 years. I don't really understand how it survived so long, but it did. It just kept on going with this extremely low gravity for 2 years through the charts. And one thing we did, actually, when I started the project on gravity, we expected the trajectories to be more like an infectious disease, as we heard in one of the other talks before. That we expected there to be social contagion of songs. And it turns out there isn't very much social contagion in songs. It's actually the best way of thinking about songs in the pop chart is the record company take all of its power and throw the song as hard as possible up into the air, as high as possible as they can. And then we decide the gravity of that song afterwards as it drops back down again. So there is very little social spreading of songs in the pop charts would be my contention. But this brings me to my next study. This is social contagion. This is a study we did on small groups of people listening to seminars, a bit like you are here. This is groups of undergraduate students, and they've been asked to listen to an older undergraduate student give a presentation, and they think that they're grading the older undergraduate student on their performance and so on. But what they're actually doing what we're actually doing is filming their applause behavior afterwards. So here they start to clap, and you'll see that she starts to clap first, then the second girl there starts to clap, and then finally he starts to clap, and there's another one who's clapped over there. And you also notice the order at which they stop clapping. So she stops to clap first, then the middle one stops to clap, and then he stops to clap. So our question was this: to what degree is the social contagion in the clapping? And so what you can do is you can plot the data like this. This is time on the x-axis, and this is the proportion of people who are clapping. You see the first clapper there, then the second clapper, and then there's this sort of sigmoidal growth shape here where a lot of people start clapping, and then there's a leveling off where 4 seconds later there's one person who's been a bit slow in their clapping. And this is also how they stop clapping. What these dots show you is each point in time a single hand clap. This is overall over a lot of different, or 12 different experiments of this type. This is the black line is the starting clapping, the red line is the stopping clapping, and the green is the growth and fall of clapping. And what we wanted to do is test, is this a socially contagious spreading of things? And we use this SIR model: susceptible individuals, people who haven't started clapping, infected individuals, people who are clapping, and recovered individuals, people who have stopped clapping afterwards. And we tested a load of models. I won't go into the detail, but it turned out that this was the best model. This susceptible, infected, recovered model was the best model to explain the observations that we'd found in the data. But there was a kind of variation of it. It turned out that if you have a disease, you don't get better faster because other people are getting better faster. But in clapping, you stop clapping because other people have recovered from clapping. So the more people who have stopped clapping, the more quickly you stop clapping as well. One of the other nice things you can do when you've created a simulation model of something, you can ask these kind of what-if questions. And the question we asked is, well, if we run this simulation 10,000 times, how long bouts of applause do you think we'll get? And we got this quite nice conclusion. What this is a histogram of the length of applause. And you'll see that most of the applause lengths were about 10 claps long, that people clapped 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times. But sometimes there was people clapping up to 20 or 30 times in these simulations. Now, of course, these simulations don't depend on the quality of the talk or anything like that. So what we found is that sometimes these bouts of clapping would go on for a long, long time, not because anyone had given a particularly good talk, but just because people, the simulated people, weren't very good at stopping their clapping. So if you do get a long bout of applause after you've given a talk, it might not be because you were particularly interesting. It could very well be because your audience aren't very coordinated. So that's something to watch out for.